Hey guys, I hope you're well. It's Dr. D. We've been talking about probability for a little while, so if you're just joining us, where we've left off is we studied descriptive statistics for a while, where we learned how to use both tabular and graphical methods as well as numerical measures to describe samples and populations. And that's useful. I described it as the place where we begin and where we end with statistics. Where we'd like to go in order to do like the driving analysis is to inferential statistics, and so that's where we're headed. Inferential means we're making guesses, but they're informed guesses, right? They're inferences that based on logic we can come draw some conclusions. In order to do inferential statistics, though, we're going to have to brush up on our toolkit. In particular, what we've been working on is the mathematics of probability. And where we've gone so far with this is, where did we go? We outlined random experiments. These are processes that generate a list of outcomes, set of outcomes that we can exhaustively list. And we were able to kludge that a little bit just by saying all other outcomes could be a category, right? So your favorite color, if I ask you your favorite color, I don't know who you are. Pick somebody in the audience randomly. Red could be an outcome, blue could be an outcome, yellow could be an outcome, green could be an outcome. But there are lots of other outcomes, so the last outcome we could just say some other outcome. And that would be a random experiment if I randomly chose you. Ooh, whoa. Okay, in that case, what we would have is the colors as the outcomes. And so these outcomes can really be anything, right? Any occurrence. What we did with the outcomes then was we talked about ways to assign probability to these outcomes. One other thing. These outcomes, another name for these, just to get our nomenclature down, was sample points. And we were pulling these sample points out from a sample space. So the set of all the possible outcomes was called the sample space. And so what the experiment did was it took the sample space and it spat out a specific sample point, basically. The idea. Once we did that, once we'd established our outcomes, we talked about how to assign probabilities to these. The way we assign probabilities, well, there are a few ways. One was the classical method. This is just evenly dividing probabilities, and this works well for some randomization devices, like picking one card out of a deck of cards. Every card in there, if it's shuffled properly, is equiprobable. If you pick two, that changes things a little bit, but we can assign a probability to each one individually. In addition, flipping a coin, there's a 50-50 chance of getting heads, 1/2 because there are two outcomes. Or rolling a 6-sided die, there's a 1 in 6 chance of any particular outcome there. And so assigning probability, the classical method, is one way to do it. Another is what we call the relative frequency method. This was where we assigned relative frequencies to all of our outcomes based on historical observation, and then use those relative frequencies to assign probabilities, and those would satisfy our rules of probability. And then the last one we talked about was subjective probability, meaning if there's no good data, but there's good reason to think that the outcomes are not equiprobable, then you can use what you know to the best of your ability, come up with probabilities. People are going to differ in their subjective probability assessments, so that's one of the hard parts there, is that people don't always agree, but at least it's better than not thinking about it rigorously. Okay, the last way, which we haven't talked about, is modeling, and that's what we're going to do later. Is that 1L or 2? I never know. Modeling. Yeah, 1L looks better. Modeling. In any case, regardless of the spelling of the word, we're going to do some of that, where we take a scenario and we think about it intuitively, and then try to use mathematics to describe that situation with a model. And that's where we're going to go next. But first, in order to do that, I want to draw your attention to some regularities with these outcomes. So some of these outcomes, for example, were qualitative or categorical. Like, for example, I just asked you about a favorite color. But that need not always be the case, right? In some cases, we will be able to describe these numerically, right? So numerical description of an outcome. For example, if you flip 3 coins, you could have the random variable be the number of heads. That's a number, right? or if you call 5 people, the number who answer their phone. Or if you weigh a candy bar, the weight in ounces. These are all numbers, right? And so, since these are numerical descriptions of an outcome from a random experiment, we have a name for this. Of an outcome of a random experiment. The name is going to be a random variable. And random variables are really powerful. The reason they're so powerful is that we're slowly going to be working our way away from a world in which we outline these outcomes as sets, and towards a place where we can place these on the number line. We can order them, and we can do all sorts of stuff to these random variables that we could do with any other type of quantitative measure. So let's look at some examples about this. Another way just to think about this is a rule for how we map numbers to outcomes, to each outcome, right? And so let's say we have some experiments here, and I outlined a few right there. And then we have a sample space, the set of possible outcomes, and then we have a random variable. All right. So let's see, our experiment is, for example, let's roll a die. Now when we roll a die, we don't usually talk about it, but what we care about is the pips on the upper face. Right? There are other things that you could, other outcomes you could measure, right? The number of times that the die bounces before it comes to a stop, the die on the lower face, right, or the sum of all the pips on the sides. But generally, just by tacit agreement, you've done this before with other people, and it's expected that when you're making a guess about the die, or you're making and taking an action based on a die roll, what you care about is the pips on the upper face. And the possible values that x could take here, the possible outcomes are 1, 2, 3, 4, 5, or 6. They don't have to be in order. It's a set. And if we want to turn this into a random variable, it's pretty easy. We just assign x to one of these values based on the experiment. So I used a new symbol here, a few new symbols maybe if you haven't been following along. When we have a set, the notation we use to keep a set together is these curly braces. If it's an ordered set, we'll use parentheses. And then finally this symbol, which it's an operator, or it's an assignment operator. This means is in. If you use LaTeX, it's which slash, I forget the direction the slash goes. /in is the LaTeX symbol for that. But yeah, so that is an element of a set. So x is an element of this set. Those are the only possible values that x can take. Another name for this is the domain of x, if that's familiar to you. All right, now let's do another experiment, or let's consider another experiment. What if we wanted to draw a card? Well, cards have all sorts of values, right? There's the suit and the face value. In this case, in order to assign a number to it, we're just going to refer to the face value of the card. Right? Now, in a normal deck of cards, of playing cards, this face value can take a number of different values. In particular, it can take ace, 2, 3, 4, 5. Let me put these set brackets here. 5, 6, 7, 8, 9, 10, jack, queen, or king. Now we need some rule to assign numbers. Historically, if you were designing a game, you wanted to build your own game, and you were writing a computer program, you would assign values to these in what seems like a relatively intuitive way, right? Ace is going to be 1, 9, 10, jack is 11, queen is 12, and king is 13. And thus we can set up x as one of these values, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or 13. And those are the values it could take. And none other ones, right? That's that experiment. That's a model of that experiment, at least. All right, now, what else do we want to do? Let's skip ahead to the height of the next person to walk through the nearest door to you. call it that person an entrant. So the height of the next entrant. How tall could that be? Well, if we really want to consider all the possibilities, there could be really unlikely things that could occur. They'd be unlikely, but not impossible. Well, what's the shortest person that could move into the room under their own power? Let's say maybe 20 inches, right? Somewhere between 20 inches, all the way up to 8 feet tall, possibly. They'd have to duck, probably. 8 times 12 is 96, so 96 inches. And so we would just pull x from here, right? So our assignment rule, our random variable, would be x is the height in inches. Now on the ends there, that's pretty improbable. I mean, if you're watching this at home, then you probably would place a high probability on the specific height of somebody who lives near you, or at least the range of the people who live near you, or live in the house with you. But if we want to capture all the outcomes, that would do it. And this variable, sure enough, will capture this experiment. Let's see what else. We've got a few more. Let's do a business application. Let's imagine that we have a candy bar factory. And so we want to look at the total number of candy bars in a given day. In a given day. Now in this case, it could be 0. It could be 1. It could be 2. Up to the maximum possible. I don't know what it is. You'd have to do research ahead of time to figure out what that is, but there is some maximum value that a given factory could make in a given day. And here you just assign x as the number of candy bars. All right. How about slightly different? Average number of candy bars in an hour. In a given hour. Oh, average number of candy bars per minute. That's what I meant. Average number of candy bars per minute in a given hour. Right. Well, it could be 0. Or if they made 1, it could be 1 divided by 60. If they made 2, it could be 2 divided by 60, and so forth, right? Up to the maximum possible. And again, x would be the number of candy bars. All right, what else do we have here? What if we weighed a particular candy bar? That's a little different. So the weight, the experiment is to weigh a candy bar. And then, since I'm American, we'll call this ounces. It probably couldn't be 0, right? Because then it's not a candy bar. It's just it's a nothing. So somewhere between 0 and what? 32 ounces. That's 2 pounds of chocolate. Yeah, that's good enough. I mean, another way to say this about x then is if x is the weight, then 0 is less than x is less than or equal to 32. I guess this is less than in this case, and less than here because I used parentheses rather than brackets. We'll see that probabilistically it usually doesn't matter. All right. What about kind of a quirky example? Let's just say that you are working somewhere and you're going to get a phone call from a customer, and we want to know what the gender of your next customer is. Can we do that quantitatively? Well, as long as we have a number that measures it, we can, right? So we could have what? Male, female, or if we ask them at point blank, they might prefer not to say for lots of reasons, but those are possible values, right? So in order to assign a number to this, we would just have to have some rule, right? X equals 0 if male, 1 if female, otherwise 2. Right? If there's missing data, and certainly when we deal with data, a lot of times we have demographic data like that, and we need to assign numbers somehow, right? Some kind of code, and so we do that. Later on, when we get to regression, we'll learn about how to deal with this kind of data. But for now, it's good to notice that we can do stuff with this, right? All right, so that's a lot of possible experiments. Now, I kind of want to draw some attention to, what's going on with these. In some cases, there's very specific values that can take place, right? For example, when we roll a die, you can get a 1, a 2, a 3, a 4, a 5, or a 6. You can't get a 3.7, and you can't get a 4.2. And so we can't have values in between neighboring values, right? Intermediate values are not legal, right? The domain comes in chunks. And that's true for a couple of these, right? That's true for this one. That's true for drawing a card. You can't get an ace and a half. Where else? The total number of candy bars. Even this one, an average number of candy bars, per minute in a given hour. I mean, the total number of candy bars in a given hour comes in chunks. And in this case, we just divide those chunks by 60, but they're still chunks. Now, in this case, they're decimals, but they're still decimals that come in discrete chunks. Same thing with the gender of the next customer. On the other hand, we have a few of these, like the height of the next entrant, or like somebody very much could be 38.247351722 inches tall, right? Or in between 37 and 38 inches. Similarly with the weight of a candy bar, right? Anywhere in between here is fine. 1.4 ounces, 3.7 ounces, pi ounces is a possibility. And so we have two varieties of random variables that we're going to have to treat differently. One set of these is called discrete. They're discrete random variables. They're called discrete because they come in discrete chunks, right? They come in chunks. So that's the kind of way to think about this. It doesn't matter what size the chunks are. If they come in chunks, in even chunks, then it's a discrete variable, right? So this discrete random variable, in this case, the domain does not contain intermediate values between neighboring values, right? If we plot these on a number line, it's gonna be Swiss cheese, right? You're gonna have a couple dots, and then there's gonna be holes. On the other side of this, we have continuous random variables. For continuous random variables, these come from a continuum. These are drawn from a continuum. So the domain is smooth. And the truth is that if you zoom in far enough, right? I mean, at some point, you get to how many atoms does a person have, and that's a discrete number. It's effectively unknowable, right? And so the weight of somebody, for our purposes, is continuous, right? And so we're going to treat these very differently. The reason why we're going to treat these very differently is because the probability of a specific outcome here, the probability of, say, 1, it need not equal 0. Right. In this case, the probability of a specific value, so the probability that somebody's height equals 60 inches, well, it's worth keeping in mind that when we say their height is 60 inches, we mean 60.00000000 inches. And the chance of that happening is vanishingly small. And so this is effectively 0. So when we talk about continuous random variables, we're going to talk about the probability of a range. For example, the probability that somebody's height falls between, say, 55 inches and 65 inches. Right? They're 5 feet tallish. On the other hand, when we talk about discrete random variables, we'll talk about specific values. Now, the beauty of this is that this will allow us to do all sorts of things mathematically. Right now, we're talking about numbers, and we can do things to numbers. We can put them into functions. We can, take integrals over those domains if they're continuous and stuff. We can sum across them, and so that's where we're going to go next. So this is just kind of a brief primer on random variables, on both discrete and continuous random variables. Again, a random variable takes these random experiments we've been running, and then whenever we can come up with a numerical description of that outcome, we call it a random variable. Usually we call it x, and then we can do all sorts of stuff to x. We can specify its domain, and we can classify it as either discrete or continuous. Next time we'll talk about probability functions and how we assign probabilities to random variables. Thank you, guys. Remember, it's Dr. D. If you have questions, you can leave them in the comments below. And if you have any requests for videos you would like to see, please let me know. I'll be more than happy to put something together for you. Thank you, guys. Bye.